Hello, Bastien.
Sharing my screen. How do I share my screen?
Share screen right.
Yeah.
Oh,
Manage
okay,
participants.
So you're gonna see share screen here.
The green.
Yeah, the green.
okay. I have to share the. Hi everyone.
Yeah, I think
Okay.
they can hear.
Okay, so Yemi has done most of the introduction. So I'll be giving a very brief overview of what is a very complex subject. So if it's too, how do I say it? If it's too simple, it's because I've tried as much as possible to simplify it. But to motivate the talk about global circulation, what I'm showing this real-time video, which is showing the surface wind current in real time, actually. And you can see here as the video shows that the Earth is a giant ball of fluid, actually. It's, apart from where we have land, the atmosphere itself, it's fluid, and the ocean itself is fluid, and everything is moving also. The equations, the fluid dynamical physical laws are all applicable, and we have, as a result of that, we have weather patterns, we have response to global warming, we have internal variability, and all of this. In order to understand them, it's really difficult without using climate models. So climate models are basically a way to understand the laws or the governing this motion, the motion in the Earth system, and the patterns and the variability that comes along with them. And now they also respond to external forcing, basically. So can I share my PowerPoint now?
Yeah.
I need to unshare that. And
No, you just go move over to.
it's not showing that.
Yes.
Oh, no share. Okay.
No, okay, okay.
No, it's
Okay.
okay. So based on that motivation, the climate models are basically a mathematical representation of the climate processes and interactions. That they're based. Those interactions are based on the physical laws of or the equations rather that the climate models represent are based on the fundamental physical or chemical laws, or even geochemical laws. And the basic idea is to discretize these fluid dynamical equations and integrate them forward in space and time. So the schematic here is showing the discretized Earth, the discretized Earth, where you have different grid points, and you can solve these equations in each grid point and solve for variables like temperature and pressure, and then the motion also in there. And the physical processes that can possibly, there's so many physical processes that can be occurring at the same time in the grid point, as the square box below there is showing. We can have advection is the main part of it, where the fluid motion moves, advect temperature, salinity, or even moisture around. And then you have transfer of exchange of heat, momentum, and water between at the interfaces between the atmosphere and the ocean. And then you have the main forcing for the system too, which is solar radiation and the back radiation from the Earth itself. You have subgrid processes like convection, precipitation, and that also occur in between. And for those processes too, the chemistry is also important, because the aerosols are also very important for those processes. In the ocean too, you have biogeochemical processes too that can that feed back into the system. And then you have sea ice also that also play a role and land ice and snow. So it's a very complex interaction that occurs within the Earth system. So a climate model is a way of trying to represent this based on the physical laws that we know, basically, to try to understand how these processes interact and then feedback on each other. So here is showing a very simple schematic also of what happens within a grid box. So in one grid box, for example, this grid box the main goal is to understand how the properties, the physical properties like temperature, the velocities, the mass in that grid box communicate with other grid boxes. And you have to solve for the velocities inside that grid box. And also, they are also based on how many grid boxes you divide the Earth into, then there are also processes within a grid box that you cannot resolve. And those processes are parameterized. For example, convection or a small scale weather system might not be large enough to be resolved in a global climate model, for example, depending on the resolution. So resolution is a huge part of global climate modeling, as this picture shows. Like the smaller your grid boxes, the better the easier you are able to resolve the processes that you need. But then there is also the problem of the computing power, because you have so many points that you have to solve this equation on, and you have it's not the computing power you need for these models are getting increasingly more expensive. Like this is showing the generation of climate models from the 1980s, how the resolution have increased over time. And now we have very, very high resolution models, but they are really, really, really expensive. So I will, for the next, in the next slide, I will just talk about each climate component, which are basically coupled together in the global, in the Earth system model. So the main components are the atmospheric model, which is both the ocean and the atmosphere actually are the dynamical components that you have. You have the land model also, which is land sea ice and land ice, which are not very, which are solid. So there isn't any, that the horizontal motion within this component it's negligible. So most of the equations are just integrated in the vertical direction. And then the interactions between all these components, for example, in the atmosphere, you have the time scales of interaction rather in the components are very different. In the atmosphere, you have very fast time scale variability and changing weather patterns that can occur within days and hours and disappear. Whereas in the ocean, you have longer time scale patterns, which can even span the whole globe too. Sometimes the ocean circulation, it's because of the very large heat capacity of the ocean, it can integrate the noise from the atmosphere over longer time scales. And also recently too, we worry about sea level rise because of global warming. The ocean also influences that. And then the land model, mainly what they try to model is the soil moisture and the interaction with surface between the atmosphere and the land, the surface roughness, or the interaction with evaporation or evapotranspiration, and how this feeds back into the atmospheric circulation. Also, the CO2 exchange with the atmosphere too is also modeled in the land model. For sea ice, the major component of sea ice that really affects the climate system is the albedo, because the sea ice reflects, at the polar region, sea ice reflects a lot of the solar radiation that is coming in, and a lot of studies or modeling have gone into studying the impact of the changing or with global warming, sea ice is reducing, and we're trying to understand how much of that change in loss of sea ice is affecting the net albedo of the system, and how much heat can be taken up by the Earth system as a result of sea ice changing. So, and sea ice also interacts with the ocean model, because that's where the change it from liquid to solid comes from the ocean, basically. And then you have those with land ice too, ice sheets that if they melt, there can be a huge impact also on the on sea level rise. And then there's also the river. Sorry, I did not complete that sentence, but there's an interaction also, river models too, that try to implement the amount of runoff into the ocean from rivers and nutrients that can flow into the ocean from that. And there's also the biogeochemical component of that, where nutrients and marine life can also feed back into the circulation or the global, have an impact on the global climate response generally. So it's, as you can see, it's a really complex system. So I will just talk mainly on the atmosphere and the ocean components, which are the most the dynamical components. They take the largest, they are the most fluid part of their system. So for the atmosphere, the main source of energy into the Earth system is really through the atmosphere, through solar radiation. And then you have, in terms of solar radiation, you also have the shortwave radiation coming from the sun, and then you have long-wave radiation, and all this also interact with clouds. And at the end of the day, you have to the net radiative transfer. There's a model component that calculates the net amount of radiative transfer heating that you have for each grid boxes, so to speak, because of the gain through short wave, loss through long wave, and scattering with clouds and all of that. And then the dynamical component is where the fluid dynamical equations are solved. This is here, I'm only showing 3 of the equations that are solved for in each grid box, and it's mainly solving for the velocities, which is in the XYZ direction, based on the temperature, the Coriolis force, the gravity, and then the pressure changes in the grid boxes. And then the pressure changes are dependent on, of course, the temperature, and then the density also of the mass too. So it's these 3 equations are solved for at each grid point to determine what would be of course, there is moisture, also humidity, that plays a role also in the net energy balance in each grid box. So each grid box solves for this, determines the velocity, and communicates that with the next grid box, the transfer of energy from one grid box to the other. And then the smaller scale processes that are smaller than the scale, the spatial scale is smaller than the size of the grid box, are the sub-grid scale processes that are parameterized. For example, convection and aerosol cloud interaction. I think Yemi can say a lot more about that than I can. So basically, that's what goes on in the atmospheric model. It's much more complicated than that, of course, but it's the bottom line is that each grid cell computes all of this, solves for all of these variables, and then the transport from one grid point to the next is the communication between each grid point, and then the sub-grid scale processes, the parameterized variables are also added onto it, the equations to give a good estimate of the changes that is occurring within the grid point. And then for the ocean, the main source of energy input also is the solar absorption, and also the air-sea flux exchange at the sea surface. with the atmosphere. And the AC flux exchange is mainly in terms of heat, which is also long wave exchange, latent heat, sensible heat, and also there's exchange of freshwater fluxes, which can come in form of precipitation or even melting from sea ice or sea ice growth also. And then a major component of the exchange with the atmosphere is the wind steering of the ocean circulation. So the surface winds from the atmosphere, the momentum is transferred also into the ocean current, and that forms a huge, the wind-driven circulation in the ocean is a huge component of the ocean-driven circulation. And then you have the thermohaline-driven parts to where the density changes in the ocean through the heat and freshwater fluxes affect also the overall circulation. So the equation of motion that are solved for in the ocean grid boxes are similar to that of the atmosphere, but in the case of the ocean, you have salinity, which affects the density and which determines also what the density, the buoyancy-driven circulation would be. So the grid cells, you basically solve for the velocities and how temperature and salinity change within each grid cell. And then there's so many other subgrid scale processes that are not resolved by these equations, like convective mixing at the high latitude, and then there's vertical mixing between the ocean density layers, and there's diffusion, horizontal diffusion by eddies, and also just eddy diffusion along isopycnus. So all these processes are parameterized also in the ocean model and added onto, those terms are added onto the main dynamic equation to solve for what the large scale circulation or transport will be in the ocean. So this is also a very simplified way of looking at it, but it's I think it gives the overview. If you have any more questions about,
I was just going to say that if you have any question as she's talking along, please don't hesitate to just say your question so that she can, maybe address them as she goes along.
Okay, I guess I'll continue. So now the main component of the climate or of a net system model is the coupling between each individual component. So the individual component, as I mentioned before, there is exchange of fluxes between the components. So for example, the atmosphere and ocean, the main dynamical component, they exchange momentum, heat, and freshwater fluxes. And then the ocean exchanges heat and melt and surface stresses with the sea ice. The atmosphere also exchanges radiative fluxes. The albedo from sea ice is also transferred to the atmosphere, because then the atmosphere, the amount of solar radiation that is reflected by sea ice also plays a huge role in determining the net radiative transfer in the atmosphere. And then the atmosphere also transfers some turbulent fluxes like sensible heat and latent heat fluxes to sea ice. For land too, the atmosphere exchanges heat, freshwater fluxes in terms of precipitation with land, and then the surface turbulence at the boundary layer too is determined by this exchange with the land model. So the coupler is mainly the model component where the fluxes that is exchanged between the models are computed. And you can see the atmosphere showing in this schematic shows the atmosphere model, the exchanges, it's in I think purple. So it passes fluxes to variables to the coupler, where the coupler computes the necessary fluxes that will be exchanged. And the atmosphere is the main component that really exchange fluxes with every other model. Some other models don't necessarily need to exchange, like the land doesn't exchange anything with the ocean. Well, it does exchange some, but maybe in terms of runoff. If there is sometimes the river there's a separate river model that computes runoff, but in some cases, maybe the land model is used to compute that. But the atmosphere is the main component. The ocean exchanges fluxes with the land ice and sea ice and the atmosphere mainly. It's really this is what I was saying. The ocean doesn't exchange fluxes with the land model, for example. So, but all this exchange of fluxes are timed in such a way that the atmosphere model is integrated forward in time, the ocean model is integrated forward in time, sometimes in parallel, and the exchange of fluxes is done at a time, maybe once daily, depending on the resolution of the model, or every hour, or depending on it depends on the resolution of the model and the time, also the time increment in each model. So the forcings, I forget to mention this, the main forcing of the climate systems are usually in the atmosphere. For example, with the solar radiation and for global warming, the changes in greenhouse gases and all of the natural emissions are usually within the atmosphere. And then the atmospheric variables change, and by exchanging fluxes with the other model components, the other model components also respond to that, and then the response is also passed back to the atmosphere. And at the end of the day, you have this series of feedback processes that are going on in the climate response. So there are simpler configurations that are different from the global coupled or fully coupled model that the schematic just showed. And these are mainly, you can run the atmosphere, the called standalone simulations or models where you can run the atmosphere alone or the ocean alone, or you have a slab ocean model. And the basic idea is to treat the other climate components as boundary conditions. For example, all the atmosphere would care about from the ocean is the sea surface temperature change. So for an atmosphere only model, it's the full atmospheric model, but with the boundary conditions from the ocean, as in terms of SSTs are prescribed, of the land changes to are prescribed. So you don't have a dynamic ocean responding at the same time, but you fix the boundaries and see what happens. And this standalone simulations are useful for studying process to understand like what drives what. Is it the atmosphere alone that is driving a particular climate phenomenon or variability, or what? It's a way of testing what drives what within the climate system. So if you remove the response from the ocean, for example, you can tell if you still have El Nino, for example, you won't get El Nino in an atmosphere only model, because it's a coupled mechanism. So it's ways like that they are tested. And the slab ocean model, the ocean model rather, uses the fluxes you normally receive from a coupler in the fully coupled model. Those fluxes are prescribed, so that you can run the ocean alone and test what the ocean does on its own. For the slab ocean model, the ocean is, instead of, it's similar to the atmosphere only model, but the ocean is reduced to only a slab layer, just the mixed, the top mixed layer of the ocean is given to the atmosphere. So instead of prescribing SSTs, the SSTs are computed from the mixed layer response. So instead of what is prescribed in this case is the ocean heat convergence, or the heat transport that the ocean would have in an ocean, if you had the full ocean model, would be prescribed, and then the SSTs are computed from that response. And then and they're also useful too, because the standalone simulations have a lot of limitations, because of course in the real sense prescribing boundary conditions, you necessarily remove feedback processes, and the response you get is not necessarily realistic. So in order to avoid those complications, the slab model, for example, it's a good bridge between that. And then we have the regional climate models too, where you can zoom in a smaller region in the globe instead of simulating the climate change, the climate in the whole Earth system. You can zoom in on the smaller part of the globe, but then you have to prescribe the boundary fluxes probably from using inputs, getting the boundary fluxes from a global climate model. But then the advantage is that you can increase your resolution and you can understand the local processes that are not resolved by the resolution in the global climate model. So I think that sums it up. I think for the next, this slide, I'm just talking about the possible. I think I've mentioned most of them too, what we can use climate models for. They mainly used to understand the mechanism of climate variability and change, which we can't understand this otherwise if we use observations or the only way we can study what climate component does what is if it's basically our laboratory for removing one component in order to understand the effect or to understand what drives what. That's the main, for me, is the main use of the climate model. And of course, we can use them for climate projections. With global warming, there's so many changes that we don't know how the climate will respond to, but you can test that in the climate model. You can quadruple CO2, you can double CO2, you can combine the emissions and see what are the possible rates at which the surface the Earth will warm over the next 100 years, for example. There's no way we can do that otherwise if there are no climate models. And then we can have weather predictions, which are more short-term predictions and affect more smaller scale changes also. And that, I think, is the most common, most widely used or used for climate models too. So I think I'll stop there and
thank you very much, Dr. Garuba. That's a very good one. Anybody have any question before questions? Well, I can start. So I realized that the number of people were joining in during the talk. So I understand that you may not have heard everything that she said. But I can give you a quick summary why we're at it and why maybe people are preparing their questions. First of all, before I go ahead, I should say that if you want to ask questions, you probably have to unmute yourself in case your maybe phone or computer is muted, and that way you can then connect and say and probably say your question. So just a quick summary for people that probably were joining inside. She is talking about a general overview of global climate modeling here. So the kind of a toolbox that you need to simulate what is happening in real world. And it's rather complicated, but she's done a very good job to try to break it down into the simple component of things that we need that goes into these climate models for us to understand it in general. And like she said, for example, if you want to simulate the clouds that's happening over your house, for example, it's much more difficult to put that into, say, mathematics and equations that you'll be able to get a couple of numbers for you to be able to simulate and show that, okay, this is the nature of cloud that's happening over my country, over my region. And for models to do that, they have to discretize it into several different boxes and said, okay, for each boxes, we're going to try to understand what's happening in that box. Then actually she rightly mentioned, sometimes those boxes can be bigger than what you actually want to simulate. For example, the clouds over your house. So the box can be bigger than the cloud over your house. And if you have to simulate that, you have to probably parameterize by just assuming some random numbers for that particular box or for that particular cloud. So it's kind of like some of the back of the envelope gimmicks that people do in climate models. And she also go on to mention that, that there are several components that goes into these Earth climate models. One of them is the atmosphere. So there's a whole part of the model that deals with atmosphere simulations. There's a whole part that deals with the ocean simulation. There's a whole part that deals with ice simulation. And there's a whole part that deals with land and river runoff simulation. So So it's a really big stuff, but there's a small components that do different things within the same model. And she went on to talk about how each of these components can also stand on their own. You can run them individually. You can run two of them together, or you run three of them together if you don't want to run everything all together. So it's rather complex, but it can be simplified in a way that still allow you to understand some simple phenomena. Like for example, if there's a big hurricane that you want to study, you don't really need all the earth system models to study the hurricane. You only need the atmospheric model. And then for you to be able to understand how the ocean is impacting that hurricane, for example, you can specify what the ocean is doing without necessarily running the ocean model. So it's some of the ways to bypass trying to run those complicated, complex model without try to still understand what's happening in nature. And she gave a couple of example applications like that she's showing here in the slide that, for example, you can use those models to run your climate variability change. So exactly how your climate is going to change from year to year. You can also study what is going to happen 100 years from now in terms of your climate or weather prediction, things that are happening around your area. So that's kind of like the general overview or summary of what she said for people that probably was doing us somewhere in between. So, Yemi, Kunle, go ahead.
I just wanted to say thank you to Dr. Yemi for that very concise presentation. I know she has actually done a lot of work in trying to compress a very complex situation into something very easy and simplified for everyone to understand. I particularly enjoyed your talk. Thank you so much for that. I just want to make some few comments and probably ask for your contribution as to the fact that these climate models are basically kind of coerced models because we are limited in terms of our computational ability. So we cannot resolve every grid scale. So speaking for the ocean, for instance, probably you are coupling an ocean of say a quarter degree to your atmospheric model. There have been current research that have shown that there are other small scale structures that have not been resolved by these ocean models that are actually having strong impact on the climate projection. And these kind of structures have been parameterized, and this parameterization are not very effective in capturing their real effect on this climate projection. So my question is, what are your thoughts as to how do we bridge this gap between the fact that we don't have enough computational resources to actually simulate these skills and the fact that we are missing out on the quality information as to the role these very small scale structures are playing in terms of climate projection?
Yeah, I think I glossed over it. Like you said, the computational cost is very expensive, but there are more and more climate efforts towards high resolution modeling too, that are being done in order to see what are the impact. For example, the E3SM model too is one of the high resolution modeling efforts that is going on. And I think at the Ocean Sciences meeting, there are so many things that are done to at least show how big, if it's, of course, we can't run those high resolution models as often as we would run the low resolution simulations. But if, I think we need a couple of those simulations regardless to be able to say, this is what mechanism we're missing and improve parameterization. We definitely, I don't think the parameterizations are perfect, but with high resolution modeling, we can improve the parameterization. The goal is to reduce uncertainty as much as possible. So if some efforts are going into doing high resolution modeling, taking the lessons we learn from that to improve parameterization, I don't think we'll ever be able to run high resolution simulations as often as we would like to. So we still need those parameterizations. So I think the main goal will be to understand, improve the parameterization. For example, the main goal will be to improve parameterization.
Yeah, thank you for that. Still speaking on this subject of parameterization, I don't know if you are aware of these data-driven approaches in which whereby there's been this growing community of people trying to use machine learning algorithm to try to, as a basis to parameterize these sub-skill features that we're not resolving. So the question arises again, you being an expert in climate projection, how accurate or how do you see, how effective do you think these machine learning algorithms are in terms of replicating the real physics of this sub-scale parameterization? Because we know machine learning as it is, it's more of a black box.
Yeah.
You give it some bunch of data set and it gives you whatever you want depending on the data that you provide. So how do you think, is it a true representative of the physics going on in this simulation?
I think to me, machine learning is like it's a statistical tool, and the limitation with statistics is it tells you the patterns. It doesn't tell you why the patterns are there. So you still need to understand put a number. You still need the physics regardless. So you can even the machine learning, you can, for example, train your data, your algorithm on a behavior that is maybe on a sample set. Does it carry over to a different data set? You don't necessarily know. If you train your data on maybe the variability in a climate change environment, would the same pattern still evolve? Everything is changing, So we still need the fundamental, we still need to understand the physics. So it's a powerful tool. I do not deny it, but we can't ignore the physics and just rely on it. Like any statistical tool, it will tell you, I can tell you a number of studies where statistics will point you for example, the AMV debate that you get in some statistical study will show you, oh, the atmosphere is what drives AMV based on predictability study. You get very good predictability using a slab model to predict it, the AMV. But if you really study the mechanism of it, it's really the ocean that is causing that. So things can get confusing if we rely mainly on statistical tools.
Yeah, I think I can also add to this a little bit. Yeah, I think you're bringing a very important point. So, like, I think you're mentioning there's a lot of deficiencies in the current models that we have. So it's one, it's big, it's huge, it's humongous. The other is the resolution that you're mentioning. So there's a place for obviously data-driven
approaches,
machine learning to fix some of these things. And for people that may not know, that you've been hearing parameterizations. So what he or they mean by parameterization is just some kind of crude assumptions that are made in some of these models that are not necessarily physics. So the way these models are built up is because they understand the physical relationship between the wind and the cloud, for example, or between the water and I don't know and the atmosphere. But when they don't understand physics, they try to just put some numbers there or some kind of assumptions there to represent what they think nature is trying to do. So that's what parameterization means. But what he's trying to ask is that, okay, what can you do when you have data that you directly measure from nature to kind of fix places where you're having to assume what the nature is trying to do? So there are, of course, some room for that. But what Yemi is also trying to mention is that why some of these things cannot necessarily be easily done by having to train data train your model based on data that you have. There's still room for physics to actually drive the basis of it. And why there are some deficiencies, maybe not. Data-driven machine learning can help to solve that. But again, I think there's some part of it that will be true. And if you ask some people, maybe they agree. Yeah.
I think we're moving towards this direction whereby we'll probably be using a combination of both this data-driven approach and our knowledge of physics to actually come to a point whereby we can reliably resolve these small-scale processes with less computational resources, given that we have data sets from the real ocean or real atmosphere.
That's great.
Yeah. I don't know if people. Yeah, everybody is defending their, what they do. But I think.
No, I'm absolutely on the same page with you. I'm just saying that there's a potential here. I understand that there's a big problem with the parameterization that we know for now, there's a big problem trusting machine learning as it is, because it's just garbage in, garbage out, depending on how you tune it and the hyperparameter that you suggested. Yeah, I'm just saying that we are moving towards an area whereby it's going to be more coupled now. Instead of an atmosphere-ocean coupled, it's going to be like an AI coupled Earth system model. That's just my point.
Yeah, no,
that's a good point. Yeah,
let's move on from
that question. Yeah,
okay.
Maybe some other people have questions. Yeah, before we go. Yeah, any other question before we get boiled down in AI?
Now we have some question in South Africa.
Yes, please go ahead.
You want to ask again? He was asking about the uncertainty on the model, and what I would like to ask is, at the beginning you show a model. I would like to know if you can tell us a little bit more about what models are available for free. And in our field, in my field, we are trying to understand how the Earth has evolved due to past climate change. So I would like to ask a question about if there are models that are available for the past and not for the future, and how does it work?
Yeah, I'm not a paleo expert at all, but I know people are doing studies in that. I don't necessarily know if they're using modeling, but they're using observations to reconstruct what the past climates would be like. I don't know too much about paleo.
Do you know about this?
Vaguely. So this is anecdotal. I can't reference any papers, but I do think that people play with like landmass. So say you can run like a GCM with Gondwana instead of the current like landmass distribution. People have done things around the Ice Age, snowball Earth.
Yeah.
Snowball Earth, and try to figure out how you can get into a snowball Earth, how you can get out of a snowball Earth through global climate model feedbacks. But I do think because there are so many uncertainties around some of the differences in the physics that may have been, and some of the differences in like the geographic distribution of landmass and stuff like that, people do tend to use more experimental and observational methods. But you guys know that, I'm sure, down in South Africa.
So I don't know if that answers the question, Bastien, but I think you also asked about uncertainty, right?
If I can precise the question, if we don't go too far back in time, can we run a model live from the 1980s to today? Is it something that's available online for?
Yes. Online. You mean online?
You mean output or?
Okay, so I don't know if I understand your question. So if you mean like to be able to run model remotely on the website, is that what you're trying to ask?
No, I'm checking the weather for next week. I can do that online, and I can see new Earth. I can see in the future. But I would like to know if there's the same model but reverse in time, and we can see in the 80s what was the climate in South Africa.
Oh, I see. I'm not aware of a particular tool that you can run online to check the climate of the past. But I know that there are, say, reanalysis data sets, so models that are already been run for the past time, and the data has already been saved up. And you can look at those data to figure out what the climate in South Africa was, say, in 1970, for example. So models have already been run for that time, and then they store the data, and then you can just take that data and then look at what the climate is at that particular time, in 1970 or whatever, 1960 something. But if you're really interested in, say, paleoclimate or things that are a little bit to the past more than that, then you probably have to get the data set and put it on your own computer, in this case maybe for your students, and then run it back in time. So to be able to run it back in time is similar to what she was explaining earlier, where you run it forward in time. So when you run it forward in time, you prescribe what the current climate is, and then you ask the model to tell you what the future climate is going to be, maybe in 2100 or something like that. But if you want to run it back in time, it's the same thing. You give the climate right now, and then you ask the model what happens 1,000 years ago. and then the model will tell you, the model will run, and then it will tell you what's about, what's happening in that time. But if that's what you're interested in, I think you have to probably do it yourself rather than finding that information online. However, if it is something as close as say 1970, you can find data sets that will tell you what climate is at that particular time, and then you can, rather than running the model, then you can check the output of the model that was run for that particular time. I don't know if that answers the question.
Oh, yes, thank you.
And a huge component of running back in time is knowing what forces were,
Yes.
how the forces have changed.
That factor does happen.
So if you don't know, like now we know CO2, we've been measuring CO2 for the past, God knows when, but if we don't know how it has changed in the past, there's a huge uncertainty with running backwards in time when we don't know what the forces are necessarily.
Any other question from Bastien's group? Anybody else? You can unmute yourself, by the way. Everybody's muted here. Or you can raise your hand and I can unmute you. Go ahead if you have questions. Okay, I thought you wanted to ask something like that. Okay. All right, so somebody, Elise, am I pronouncing that right?
Yeah. Hi, Yemi.
Hi, how you doing?
I'm doing good. I'm Elise from France. I'm a geoscience and remote sensing scientist here. And I have two questions. I didn't follow the presentation from the beginning. I would like to know what is the data set the doctor is using for her research. The second question is, are the articles published on her research that we could use her data set and run the models here in France so we can confirm our results? Because there was a very good question concerning AI and a real-time analysis. I think that could be done with satellite images on forests. So I believe it could be done too on Earth observations. And those were my two questions, please.
Okay, my research is mainly very idealized. I've run mainly showing the drive. My research is mainly focused on understanding the mechanism of or drivers of climate variability. So most of what I've done is done with CO2 quadrupling experiments, which are not realistic, and I've not even tried to. It's just mainly to understand the mechanism of variability, because there's still a huge part of the Earth's climate system or climate interaction that we don't understand, like the variability, how the ocean feeds back to the atmosphere and the atmosphere drives it in return. So that's what I do mainly. So I necessarily don't, I think I'm now beginning to try to apply what we learned from this 4 times CO2 experiment into historical simulations, but most of my research has been based on idealized experiments.
Alyssa, does that address the question?
Yeah. And during her experiment, did she use any machine learning algorithm as it was stated by all the participants?
No,
I would like to know.
I used fully coupled models, and I also do some partial coupling experiments where you can remove some part of the response of the ocean just to understand how the feedbacks between the ocean and the atmosphere works. So and I've also used SLAP models too.
Yeah. And my last question, sorry for disturbing, is that are you thinking of using machine learning in your further research in days to come?
Can I ask you, are you interested in machine learning?
Yeah, I'm really a scientist, and geospatial analysts will use mostly machine learning to understand, to detect events from satellite images, and we are currently developing models for FEO at Rome, and we're really interested in people that are working around it.
Yeah, I think Kunle might be able to answer this question. Kunle, do you want to address that? If you're there, can you hear us, Kunle?
Sorry, I didn't get you.
Yeah, we have somebody else that works around this area of machine learning, and Kunle, she's the one that was speaking earlier. I wonder if he wants to address this particular question. Kule, are you there? Maybe he's not.
Yeah. He's the expert on it.
Yeah, so he was the one speaking earlier about machine learning, and he knows a little bit more about machine learning. So I think if you want, you can send us an email, and I can pass along your questions to him via email. And I think he's also there with you in France, so he might be able to maybe be of assistance with research and maybe to answer some of your questions. Sounds good?
All right, thanks very much.
Yeah, you can send us an email. You can reply to the email that you received, or maybe you send us a message on WhatsApp, whichever way.
Okay, that's good. Thanks.
Any additional question? Even if it is a comment, clarification, whatever. Again, you can either raise your hand and I can unmute you, or you can unmute yourself and speak. Okay, so our speaker is going to be providing these slides and making it available, and then we're going to upload it online for everyone to have access to it, and also a recording of this video in case you want to share it with people in your group and in your chapters, so we can make also this recording available to people and maybe some of the questions. But if you have future questions and you're maybe a little bit